Alright, so this is the second video for section 8.4, and on this video we're going to talk about the tests for convergence. And this is going to be a pretty big deal. It'll turn into a pretty big deal as we get a little further. Alright, so first things first, we looked at an example of this in the last video, and we found that this is going to converge for all values of p that are greater than 1. But for p values that are less than or equal to 1, then the thing's going to diverge, the integral. Now, what is an integral anyway? Well, an integral is just adding up a bunch of things. So we're actually not looking at just the terms anymore and what the terms do, but we're looking for what the sum of all these terms do. So if we were to integrate this, we of course are going to have to do it with improper integration. Put our b in, take the limit as b approaches infinity. And we're going to take the limit as b approaches infinity of negative e to the negative b minus a negative e to the negative 1. Now when we do that, when we simplify this a little bit before the limit, we get negative 1 over e to the b plus 1 over e. Well, this right here is going to go to 0 because 1 over e to a power that's getting larger and larger and larger and larger is going to get 1 over a bigger and bigger and bigger number, which means it's actually getting be a smaller number overall. So this part would go to 0, and we would end up with 1 over e to be the limit of this thing. Now that would also be the sum of the area, the value of the area that this thing would approach as your x got larger and larger and larger and larger. So this integral converges. But what happens if we take a negative x squared and do it in the same place? Well, we can compare, and we know that we can compare 1 over e to the x squared to 1 over e to the x for positive values of x. Well, for positive values of x, what's going to happen? Well, this one over here is going to have a larger power on top for all values greater than 1. Once we get past 1, when we square a number, we're going to have a larger number there than we're going to have with just the number itself. We think about 2. 2 squared is 4. So we would have 2 here, but we would have 4 there. We would have 4 here, but we'd have 16 there. We'd have 5 here, but we'd have 25 here. So what's going to happen to e to the x squared? It's going to get, 1 over e to the x squared is going to go to 0 even faster. So that means it's going to converge as well. And this is why. All that I just talked about, this is actually proving mathematically, making the statements to verify this. For x values greater than 1, e to the x squared is going to be greater than e to the x. Therefore, 1 over e to the x squared is going to be less than 1 over e to the x. And if we know that 1 over e to the x converges, the integral of it as x goes from, or as you go from 1 to infinity, then a number that's going to be smaller is also going to converge. So there is 1 over e to the x squared, and 1 over e to the x looks like this. So if we know that the blue line converges as we find the area under the curve from 1 to infinity, what do we know about the red line, considering the fact that it's going to get lower much faster? So we know that since 1 over e to the x squared is always below 1 over e to the x, we say that it is bounded above by 1 over e to the x. Now you could also think about this as a sandwich theorem problem, and we're sandwiching between 1 over e to the x and 0. So as this limit goes on forever and ever and ever, they're going to approach the same value. Now that's talking about the actual function value, not the sum of all these values that we're adding up. So be careful and make sure you understand what the terms do or what the function does for values is not the same thing as the integral. What the integral does is adding up and finding the area under the curve. The terms or the function is just what the function value is as x gets larger and larger and larger. So, since 1 over e to the x squared is bounded above by 1 over e to the x, and we know that 1 over e to the x converges, then 1 over e to the x squared must also converge. Now, you're going to notice that on some of these questions, most of these questions actually, it's not going to ask you what does it converge to. It's just going to ask you, does it converge or not? You can't just take a coin and flip it. There has to be work behind your reasoning why. If you don't have one of the tests that we're going to talk about, that you actually use and prove it, you will not get credit for it. Not on my tests, not on the AP exam. So if you just put converge or just put diverge and give no reason, the question's wrong. Period. Even if you got the converge or diverge right, with nothing to back it up, your answer's wrong, period. All right, now that brings us to page 464 in your book. And this is the direct comparison test. And what that means is that let f and g be continuous on the on the mixed interval from a to infinity, with 0 being less than f of x, which is less than or equal to g of x, for all x greater than or equal to a. Then we know that the integral from a to infinity of f of x dx converges if the integral from a to infinity of g of x converges. Because like we said, very much like the sandwich theorem, if f of x is always below g of x and we know g of x converges, then f of x must converge as well over the same interval. Now, if we find out that g of x over this interval diverges, it doesn't tell us anything about f of x. That's why this is backwards. Notice that these are backwards. But if we'd found that g of x diverges, if it's what we're comparing to, and we find that g of x diverges, it doesn't tell us anything about f of x. But if we can prove that g of x is always greater than f of x, and f of x diverges, then we've proven that g of x diverges. That's what this second one is. So it kind of flips on you here. Be careful. If the one above the function converges, then that proves that the one below it converges as well. That's number one. In the second part of the direct comparison test, it says that if the one above, it says if the one below diverges, then that's going to prove that the one above diverges. You can't have values that are greater than all the values for this function, and this one converge, but that one diverge. It doesn't work that way. This one essentially, if it diverges, it's going to push this one off into infinity as well. All right, so let's look at an example here. We've got the integral from 1 to infinity of sine squared x over x squared dx. Okay, the maximum value for sine x is 1, so we can use that as an upper bound. So we know that sine squared x over x squared is going to be between 0 and 1 over x squared. Now, here's a question. I want you to think about this, but I'm going to give you the answer right after it. Why do we not have to worry about sine x being low value of -1? Well, we don't because we're squaring it. So regardless of what it is, once we square it, it's going to be positive. All right, and we know since 1 over x squared converges, then sine squared x over x squared is going to converge as well. Now, you're probably trying to think, okay, well, how do we know that this one converges? Do you remember the p-test we did at the very, very start? Remember, x to the p power, as long as this power right here is greater than 1, that integral is going to converge. So since we've proven that this thing converges, and this thing is always less than it, it means that this must converge as well. All right, so what about this one? We've got the integral from 1 to infinity of 1 over the square root of x squared minus 0.1 dx. Does this thing converge or does it diverge? Well, we know that the square root of x squared minus 0.1 is less than x for all positive values of x. And this could be 0.1, it could be 0.00000000001. It's still going to be less than x for all positive values of x. So what we can do is we can compare this to 1 over x. So we know that 1 over the square root of x squared minus 0.1 is greater than or equal to 1 over x on the interval from 1 to infinity. Well, what do we know about 1 over x? Well, we know that 1 over x diverges by the p-series test, or the p-test, because x is 1 there, the exponent is 1 there. And since we know that that diverges and this is larger than that, then that has to diverge as well. All right, so what we find is that if functions grow at the same rate, then they either both converge or they both diverge. And we can use things that are greater than or less than a function for all values in the interval. It's got to be true for all the values that we're choosing over the interval to determine whether a function that's more complicated is going to converge or diverge by using an easier to deal with function that's either greater than or less than. Now, does the integral from 1 to infinity of dx over 1 plus x squared converge? Well, as x approaches infinity, the 1 in the denominator becomes insignificant, so we can compare that to 1 over x squared. So we could do the change here, and we could do 1 over x squared over 1 plus x squared over 1 over 1 plus x squared. And then we can, of course, keep change flip, and we get 1 plus x squared over x squared. Divide that into both parts. We're going to get 1 over x squared plus x squared over x squared, which is 1. Or we can do L'Hopital's rule, which is what we did here. And you do L'Hopital's rule, you're going to end up with 1. Now notice we're checking here, are these things growing at the same rate? And remember the rules for that. If you get a non-zero integer, then they grow at the same rate. If you get infinity, the top grows faster than the bottom. And if you get 0, the bottom grows faster than the top. So in this case, this is proving that what? These are going to grow at the same rate. And 1 over x squared we know converges And if this grows at the same rate, it must converge as well. All right, so of course, now if we did this the long way, or the improper integral way, we could do the improper integral and find that we're going to take the limit as b approaches infinity of the integral from 1 to b of dx over 1 plus x squared. Now this antiderivative right here, hopefully you're recognizing that. That's actually the inverse tangent. So we're taking the limit as b approaches infinity of the inverse tangent of x from 1 to b. So we end up with we take the inverse tangent as b goes to infinity, it's going to happen at pi over 2. And tangent is going to be equal to 1 at pi over 4. So this value is actually going to be pi over 2 minus pi over 4, which is pi over 4. Now understand that's the value that our area is going to approach in that way. And notice over here, if we do the same thing with the 1 over x squared, which we've already done, but I'm going to show you, I'll show you all the work again, it's going to be 1. Notice that these two do not approach the same number. So just because this approaches 1 and the two grow at the same rate does not mean that they approach the same value. Be careful about that. Just because we're using these as comparisons to prove or disprove convergence does not mean that they're going to approach the same value. So be careful. All right, and that is all of 8.4. We're going to talk a lot more about convergence and divergence when we get into series in the next chapter.